so well trained. Let's see. The way that I see it, do you have any questions, by the way? All right, so we're talking about forming. I talked about pressure casting. I showed the results. This was our pressure casting setup. And I talked about how the piston crushes the cake, and then we weren't able to run it. And Nestor developed that whole system of pressure casting. And you recall what the most important response was for pressure casting? Actually, it applies to all casting. 804, you doing better? Most important response was the hardness of the cast, right? So if you can handle it after the fact, it actually use that or pick up that material and move it sufficient stiffness to work. And I'm not going to spend much time on that. What I want to do today is wrap up plastic forming. And jumping around here, this is where we started years ago, a long time ago, in fact, because it says 409 and 509. That means that this timing was prior to when they renumbered all the courses, which you don't even remember probably. At least 50 years ago. So the story is this. I went to work for Shell after I got my PhD, and I worked in catalyst support. Actually, I worked for CRD1, which is Catalyst Research and Development. I don't know if you're familiar with catalysts. These are packed bed catalysts you use in hydrocracking. Using hydrocracking for petroleum and other things. And they also had forming catalysts, so you would go from, say, natural gas to the polymer. So catalyst was a huge industry and a huge business for Shell. And so I was brought on as a postdoc, and I worked in Amsterdam at the research center in Amsterdam for Shell, looking at extrusion of catalyst supports because it was a huge field. Right? How do you extrude this material? And so we developed a technique for characterizing plasticity. In the end, it turns out not to actually work very well. But it took a long time to figure out why it didn't work well. So this is sort of the preamble to all of that, right? The first statement seems a little silly. Plasticity is difficult to characterize, but if you look at the way that plasticity works, what you essentially get is that as you deform that material, or as you stress that material, shear that material, it deforms continuously, and ideally, it will deform continuously without cracking, for example, right? So all our forming processes, we have a few within traditional ceramic manufacturing. You could say hand throwing, right? Which is more or less where all of this started, right? And from there, we get to jiggering. And then we get to ram pressing. All of these actually start typically with extrusion, and it's commonly called tug milling. And so everything about traditional ceramics really is coupled to this idea of plastic body formation, right? And the whole idea that you could go to a hillside of clay, dig clay out of the ground, and throw a pot with it that you could use to carry water, 2,000 years ago or 5,000 years ago or whatever, is sort of that, is dependent upon that intrinsic plasticity of clays. Now, I've been here for 26 years, and I have spent 25 years of that 26 years trying to figure out what the plasticity of clay is. And before that, several years. So what we have in plasticity, which bears discussion, is that how do you characterize that material? There's a bunch of techniques developed. One is called an Atterberg test. It's called, and you take clay and essentially you roll it until you can form, snake or whatever how you want to call it, right? That's some measurement of plasticity, and you have an intrinsic ability to understand plasticity by taking clay and squeezing it between thumb and forefingers, right? And you get that feeling, and oh, okay. And it turns out, interestingly enough, that probably about at least 70% of the time, what you measure this way actually translates to how it behaves. In other words, in terms of throwing pots. So there's an innate ability to sort of detect plasticity. Okay? We define it as being good plasticity or bad plasticity. That's called a go, no-go gauge, if you're familiar with that terminology. And that is good or bad, right? I mean, it either works or it doesn't work. And that's an interesting problem because when we look at plasticity for forming processes, you take that plastic clay and you put it in the jigger and you get pieces out, then it works. I mean, it's really pretty simplistic. The problem is, how do you characterize that material that you could predict when it's not going to work properly? And I would argue that this transition from hand throwing to jiggering and more specifically to roller tool jiggering and machine forming is the transition that caused us to split ceramic art and ceramic engineering. Okay? Now, we can quibble about that if you wish, but I will win. But the issue is this, that early on in the formation of New York State College of Ceramics in the early years, engineers took throwing, right? Because you would go to a factory and you were essentially working with artisans, skilled laborers who throw pots, and a lot of the stuff that was made was done that way. You may be throwing into forms, but the issue was that you had to have some understanding of that process. And at the turn of the last century, in the East Liverpool, Ohio area, there were 200 potteries. Okay, and I was talking to somebody recently, talking about all these towns that they would have not just a blacksmith shop, but there would be relatively small towns that would have a glass factory, and they would have a pottery, and all these things were local, right? And in the East Liverpool area, there were these small potteries, and they would make something, and then they had a beehive kiln, right? A big kiln. They would blow the kiln up. When they got enough material, they would essentially have a party and fire the kiln. And the reason is that it was a lot of work. You had your friends to come, and you had to stoke coal, usually rather than wood. And you had to keep the fire going in order to heat the system up. But it wasn't like turn the gas on, ignite it, and set the program, and go have lunch. I mean, this was an event, right? And all these small potteries then were producing all this material, and everything was done by hand. The transition for us was the introduction of machine forming. Once you get to machine forming, now what you need is you need to understand how to control the behavior of the clay, whereas an artist or an artisan, right, working with clay, if the clay plasticity was off, you could compensate for that plasticity and how you dealt with the material. Right, so if it was a little bit too wet today, you could adjust for that. If it was too dry today, you would know that, and you would make adjustments. You might add water, you might keep your hands wetter or whatever in order to make that material so that you could compensate for those variations in clay. When you go to machine forming, all that goes away. And now, interestingly enough, we think about controlling the rheology for the process, but I think it's inverted. The process demands a specific rheology to work. And it's our job to try to hit that target. So that transition was that industry said, we don't need our engineers or the people who are coming out of school to be able to throw. We need them to understand the plasticity of clay so they can make adjustments so that when we go into production and when we're in production, we can control that process. And I would argue that that's the split, not a bad split, the split that happened between art and engineering that separated us into a specific engineering field. You can predict when that occurred, but it's probably sometime in the early 1930s when that split would occur. Because that was the introduction of machine forming. So the problem is that we're evaluating plasticity based on the application, based on the forming process. Jiggering and ramp pressing require different plasticity. Okay, and in fact, jiggering is a softer clay, more easily deformed, and ram pressing is actually a stiffer clay. Buffalo China actually, interestingly enough, if you look at the chemical analysis of their bodies running through the factory, you can tell which body is a jigger body and which body is a ram press body. And the reason is that there are two things that you see in that body. In the jiggering body, there's an elevated calcium level. And in the ram press body, there's an elevated sodium level. The question for you is why? It's such a great question. You understand what I'm saying? This has an increase in calcium, right? And this has an increase in sodium. So I'm sitting in a meeting, and we do this project with all the Whitewater Research Center, and Darren Shore, actually, our electron microscopist now, his master's thesis was on essentially looking at pyroclastic deformation of clay bodies, trying to understand how the deformation of that body correlated with the chemistry of the body. It turns out, by the way, that it doesn't, which is also fascinating. And I'm sitting in this meeting, and he identified, because everybody was all bent out of shape about, oh, I don't want you to have our body composition, because then you'll steal our body composition, and then you'll go into production and do a better job than we do. None of that's true. Right? So I'm looking at the bodies, and also they had a dry press body, and you can identify it too. It has elevated magnesium levels. So I look at these chemistries of the body, there's groups of chemistry. I think W was Buffalo China said. W is Buffalo China, this is the jigger body, this is the ram press body, this is the dry press body. He looks at me and goes, how do you know that? And the reason is, why calcium? Calcium makes the body a little more plastic, so they add calcium into the jigger body to make it softer. Sodium, now you're confused, right? Why sodium? Because sodium comes in with the dispersant, so they disperse the ram press body to make it stiffer. So when you disperse the body, it packs better and gets stiffer. Magnesium elevation levels in the dry press body was, now I'm sort of talking out of school, but I knew they added talc to the ram press body to improve it. So yeah, I cheated on that. So we would argue that plasticity is defined as shear behavior under pressure, and then the same factors that control suspension reality. So I get to this point, the 5 factors, all these factors must be relevant to plasticity. And I'm almost right here. Actually, I get it wrong. And what I get wrong is that number 2, solids loading, is not a variable, but is a response. So we're going to get to that in a few minutes. Okay. So what we did is, I'm going to kind of zip through this a little bit. We developed a high pressure shear cell. We developed, I'll show you a picture of it here. We developed this instrument basically. It sits in the lab still. We use it occasionally. And what it is that you have an annulus, you have a material you put in here, you apply pressure on it, and then you shear it, right? You rotate it. This arm here is set up to, it has load cells to stop the top from turning while the bottom turns. So you're continuously shearing that material, and you're looking at the drag, right, associated with that. It's really fascinating how it works, in that you actually get a shear failure in the material. And the first device like this that I built a shell for catalyst support extrusion, really fascinating data. And then when I got to clays, though, I actually had to serrate the platins so it gripped the clay. Otherwise, the clay slid, and you get slippage, and you don't get the right response. So what happened is that you would put the clay in, and then as you would shear it, it would fail and shear, and you're measuring then the shear behavior, and you can independently change the load, you can change the rotation rate. So we get essentially this. We said that this is a typical rheological responses. You have a Newtonian behavior, you have a Bingham behavior like ketchup. But plastic bodies actually exhibit Bingham behavior. So what you get is a linear increase in shear stress with shear rate, but you have a yield stress associated with that. And then we would argue that this value, as we increase pressure, this yield point here increases with increasing pressure. But that what would likely happen is that that slope would stay the same. Okay, you would increase that. And then what we can do is plot essentially this yield stress here as a function of pressure to look at the behavior of these materials. You should have seen this before, the Moore stress failure envelope. Have you seen Let me try this again. I suspect that you've seen this before. Where would you see this? When we do mechanics and materials, I assume you saw mechanics and materials. So you have your shear stress and your, what's that? You haven't seen this?
We didn't really have it. We basically just had static.
Say again.
It's basically static. Wasn't really much mechanics.
Yeah, we're changing that. Statics is great, but not static. We're dynamic. Don't take dynamics either. So this actually predicts that sort of behavior. And the thing that you have, interestingly enough, is that you are looking at the shear behavior under load, and that's exactly what happens in an extruder, right? You're pushing that material, and it actually fails in shear, and then flows into the die, and so you have a lot of things going on, but that's what happens. And there's a great example of this, really, really famous example of this is the Leaning Tower of Pisa, believe it or not, right? So what you have with the Leaning Tower of Pisa is you have this. You have the tower, right? Have you been to Pisa? Anybody been to Pisa? You have.
Yes.
Did you see the tower? There's no point in going to Pisa otherwise, which is not entirely true. But so you have this, right? And it's at this great angle. That's a little bit steep, but you have the base of this, and basically, this thing is sitting here, and it's leaning, obviously. Now you have a problem. What's the problem?
It's too far apart.
Yeah, you're the center of mass, and if this center of mass here gets outside of this base, you have a huge problem, right? And became a huge problem when a tower in Bologna actually fell over. Now the wheels come off the bus. All right, so problem is you have a huge amount of load on this, right, on the soil, and the soil is actually sand and some clay, I think, and limestone. It isn't actually limestone, it's actually seashells. Okay, so Pisa was at one point a little closer to the ocean, well, actually the Mediterranean Sea. And so you have these layered structures. You have a lot of calcium in the system. So what they did, really clever, not a good idea, but clever idea. They put these big, huge lead weights on the back, trying to pull this back. It didn't work, actually. When they did that, it actually started to tilt more. And the reason is that you have exceeded the yield stress of the soil. And when it happens, then this system now becomes plastic. And this thing was tilting. So they sort of this really entertaining thing, and they took huge cables, they pull this thing back. I mean, this thing's big. But you gotta go some point, right? You walk down the street, you come around the corner of a building, and there's this thing at an angle, and you're like, this is actually a bell tower. Highly recommend that you go. When I was there, you couldn't go up in it because they were afraid it was going to come down. So, and by the way, the problem is no one will go to Pisa if the tower's not there, right? So that's an issue. And you can't, if you stand back up, stand up straight, no one goes to Pisa, right? So you can't do that either, okay? But the solution to this problem is to reduce the pressure on the soil. How do you reduce the pressure on the soil? It weighs 14,000 tons, okay? How do you reduce the pressure on the soil? What's it made out of, you know? Marble?
Spread the base out.
Yeah, increase the area that it's covered. So the way to do this, they should have done this, but I'm not going to make my comment about this. It's rude. Okay, I'm going to say anything. Oxymoron, right? Italian engineering. All right, so what happens is when they dug all this out, had they cast a concrete base, right, to extend the base and footprint of this tower, they reduce the pressure on the soil by the increased area of the base. Problem goes away. You don't have to stand the thing up. In fact, I recommend that you don't. Right? But what you're doing is you're distributing that mass over, or that pressure over a much larger area, reducing the pressure. That comes all out of soil mechanics. This building is a great example of that. Harder Hall is a great example of that. And then when they got into these buildings along the street here, which you're on basically a slope, right? And you know what we're on, right, is essentially glacial till. This is all sedimentary till that more or less came from Canada, all right? And you're sitting on this, it's not particularly stable. We have a lot of clay underneath this. And it's a great movie It's on Netflix called How Much Does Your Building Weigh, Mr. Foster? Mr. Foster's a famous architect. And some guy in China asked him how much his building weighed. But if you think about that, you think about this building and the footprint, right? You have pressure on the soil. And this building is moving. And it's pretty much stopped moving, but you could go down this hallway and you could see where there were shear cracks in the support. The support pillars, then they put masonry around them, right? They put stone. You can see that they had cracked. And if you go down to 118, there's a big crack inside the chalkboard wants to go essentially towards harder. Okay? So all that has to be worked on when they renovate the first floor. But this building is moved because of where we sit. Now, if you think about it differently, if you took this building and made it 5 stories instead of 3, now the pressure on the soil is much, much greater. And then there is some sort of nonsense about Harder Hall, and they put, used to be the library was there, so the weight of the books is causing the building to slide down the hill. And it's like, weight of the books is small compared to what they made the floors out of and the walls. Okay? So they built School's library, which you're not happy about. But anyway, that building's continuing. This is all soil mechanics. This is soil mechanics. Right? And when it rains, like in California, it rains and the hillside goes away, that's soil mechanics. So you're changing the water content. That changes the shear behavior of that material. So we propose this. Wet systems are independent of pressure. The shear yielding stress is independent of pressure. You get into plastic, you get into dry. This turns out to be wrong. Okay, and we learned some things in the process. Turns out that this is plastic. Okay, so what you get is that for plasticity in these systems, the pore space has to be saturated with water. You cannot have an undersaturated system. You fill the pore space with water, and then what we've learned is that you need a little bit of excess water to provide room for particles to rearrange. And what's unique about clays is that they automatically generate that excess water level necessary for flow. And they do it because of the shape of the particles. Okay? So we went this way. We could get independent slopes with the same intercept, or independent intercepts with the same slope. We can plot our behavior. This actually worked, yes.
If you go back to that, yeah, where does wet go?
What's that?
Like you said, plastic goes down to where wet.
It is wet.
So it's just,
So wet goes away, but plastic is wrong.
okay, and
So-
then dries.
Dry is true. So what happens is if you're partially saturated, right, you apply load, what you do is you increase the force and therefore you increase the friction between the particles, right, and that increases the drag on the system. So it's really great for evaluating bodies which are partially saturated because you can actually see what that friction looks like. And we looked at a lot of samples. There's a whole bunch of senior theses that were done this way, and at least 3 master's theses that were done, with looking at plasticity. We learned a lot. It was good, but it turns out to be wrong. This is really entertaining. So, but we did learn something else, and that's here, and this has to do with aging. So these are just clays. This is ball clay. This is a mixture of ball clay and kaolin because that was really common. You see kaolin and ball clay mixed. This is kaolin, and then this is actually a porcelain body. And at the time we learned a lot of stuff, but these are water content. So 13, 16, 20, 22, 23. This one is let's see, 12, 18, 19. Okay, and that peak that you see is right at the point of saturation, just before saturation or at saturation. And then what happens is that once you saturate, then your pressure dependence is going to 0. Your yield stress is dropped. Does this make sense? So you saturate that system. So what do you see? You see, well, kaolin and ball clay in a mixture, they require different water contents to saturate that body. Does that make sense? Okay. And then look at a typical porcelain body. Water content is significantly lower for that porcelain body where you get the peak. So 12, 15, 17, and then 18. We're coming back down. If you go to 20, you're down here someplace. Why? Why do I require a different amount of water to saturate a porcelain body versus clay? What do you think, Ian?
Difference in surface area?
Not surface area. Adam? What's the difference between just a clay and a porcelain body. Say again. Yes, silver and quartz. What does that do for you? Pack. You now have a better packed body. A better packed body demands less water to fill the pore space. You know, and it took us a long time looking at this data to figure that out. Then have this. This is a little bit difficult to see, but this is just a ball clay and water body. So you have 13, 16, 20, 22, 23, 25. And then at this point at 25, at 22, at the peak, we measured that body D1. So you measured it as it was when it was made. And then a day later you measured it. Then 2 days later, 3 days later, 10 days later, 12, 15, 20. And then this is at 30 days. Look at the change in the slope. This point moves, 20 moves, 16 moves. Okay, what's happened?
Ionic solution.
Yes, the clay is aging. And as the clay ages and you increase ionic strength, what you see is a decrease in that cohesion stress. The body gets softer as it sits around and ages. Now, this is a month, right? But all we had was ball clay. If I bring in feldspar, then I get a lot more dissolution much more rapidly. Or if I pick a different clay, I get a lot more dissolution much more rapidly. So we're seeing the evidence for aging, okay? And let's see if we have anything else that's important. We have this. You're familiar with this slide, although not with black background, right? So this is the effective ionic strength, calcium ion concentration. And then when we looked at the cohesion of the porcelain body, it's essentially same x-axis scale log of ionic concentration of calcium, but they are in exactly the same location. That this drop in cohesion corresponds with the critical coagulation concentration. Evidence that all those colloidal interactions and particle interactions are still true, even though I don't have any excess water in the system to speak of, right? So ionic strength is playing a huge role in the plasticity of this body. So to reduce the plasticity or to make the body softer, that's the problem. In fact, you would say to increase the plasticity, not to reduce it, but to reduce cohesion, okay, you would add salt, specifically calcium. You can do it with sodium, but we're going to use calcium. So increase in the calcium ion concentration makes the clay softer, and it makes it easier to form in something like jiggering. Okay, so we did all of this, and we demonstrated this idea. This is viscosity versus shear rate. This is for a relatively high concentration suspension. The fact that we have two different particle sizes is not important. The fact is that I have a crowded system. So what I get here is while the dispersed system comes down, I get my shear thinning, and then at some critical shear rate, the viscosity goes back up. This increase in viscosity is dilatancy. What we found was that if we coagulate that with calcium, and then the calcium level is based on the amount of water in the pores, it's in the water, excuse me, not a amount of salt in the water, nothing to do with concentration. Then it comes down, and then what you see is you get this shear rate independent region, right? And that is plasticity. In other words, I'm shearing the system and I'm deforming without a change in viscosity over a shear rate range. This is my forming window, if you will. Okay, that I get, and then if I get past that, viscosity starts to go up. So if I set up the jigger and I have a certain speed, okay, ideally that speed is shearing within this range, okay, and then everything's forming. And if I go too fast, I start tearing them apart. So I generate defects. So what this shows me, and this is an alumina, right? No intrinsic plasticity to speak of. Although we're able to get intrinsic plasticity in that material by increasing salt concentration, that I can change from this to the plateau, I can change the way that material behaves in the forming process by controlling particle interactions. Okay? So this is why tap water is a better choice for making clay. Because you bring in calcium, magnesium, which you actually need to assist in the plasticity of that body. And by using tap water, you have that already in place. And that brings up a very interesting problem that is observed somewhat regularly, particularly by artists who go to school here and then go someplace else, right? They have a body here that works, and they make that body up, and it works great here, and they go someplace else with the same clay. Now their water is different, and ionic concentration of the water is typically lower because we are pretty much saturated with calcium magnesium here. You go someplace else, and they don't get the same plasticity because they're missing those ions in solution. They can artificially generate them by adding calcium chloride or magnesium sulfate, but we think that that difference is that they've gone to a place with better water. Okay, so had a thought in there that it's lost. Just zip right out. So here's the thing. This was for the past roughly 20 years. I messed around with this, and then it occurred to me that I was on the wrong track. Happens. You know, what's great about this is that when I'm teaching class, I'm still learning stuff. You have no idea that I've just changed my mind on something. So, forming processes, we would argue, are dictated by rheology. There are 5 factors that control suspension rheology, which you already know. There are 4 that control rheology. That means that the system demands certain water content. We have the illusion of controlling the water content of plastic bodies. It is an illusion. You put more water in than it needs, it's sloppy. It doesn't work, right? Because it doesn't care whether you think it needs more water. It needs the right amount of water to work. You don't put enough water, then it's crumbly or doesn't form well or it tears, right? And it has to do with changing that rheological behavior. And then the flow behavior depends on the ability of the room for particles to rearrange. So I have the 5 factors that you know. When I go to forming processes, I go to here, 4 factors. Particle concentration now, which is the water content in the system, is a response, not a variable. We want to act like we control the water content. We do not. So what you get is this packing behavior dictates how much water is necessary to fill the pore structure. Okay? If I improve the packing, I require less water to fill the pore structure. How do I improve the packing? How do I improve the packing? Yeah, if I add dispersant, I improve the packing, I require less water, right? So my particle-particle interactions are still valid. My particle size and distribution, that's the situation of clay by itself versus clay plus quartz and feldspar, right? When I do that, I get better packing. Therefore, I require less water. If I go, this morphology thing for clays turns out to be critically important. But if I have all spherical particles, I get one packing. If I get particles that are shaped and they're able to nest or fit better within each other, within the packing, right? When they start to align, I see an improvement in packing, right? This last one actually gets to go away because we work with water. So I have 3 now variables that control plasticity. Now you can argue that this rheology, the suspension being done here, is valid for non-intrinsically plastic systems, meaning that if I go to alumina, zirconia, or silicon carbide, this plays a role because I'm going to put polymers in the system, and that's changing that rheology of the medium. Okay, I'm not entirely sure that that's a valid approach, but these 3, particle interactions, my degree of dispersion, or my ionic strength. I increase ionic strength, right? I'm going against dispersion. But what happens is, in a suspension, my viscosity goes up. In a plastic body, the system gets softer. So sort of an inverse of behaviors we'll look at it that way. My particle size, distribution, and morphology. These 2, interestingly enough, are typically fixed. I have a given body composition. I just fixed my particle size and distribution. Okay, I pick EPK and O number 4. I just fixed or locked in my particle morphology. Now, if I take out EPK and I put in, say, Graulig, now I just changed both the particle size distribution and the morphology of that particle. Graulig is larger, plate-like particles. EPK is smaller, and then the aspect ratio is a little different. It changes a little bit. So you might see that a body created with Graulig compared to a body created with EPK might feel different or have different plastic characteristics. based on that clay. Why do you care? If you go into a factory and they have set up this system based on a batch, right? They've selected their raw materials. The clay companies are all about this. They want to sell you clay. What they want to do is that you're buying EPK, but that's not our product. We want you to put in top element 6, right? So I'm going to convince you that you should swap in that clay. You put that clay in, and now suddenly your overall plasticity has just changed, and you're no longer making product in your factory. Right? I know I just saved, $10 a ton on clay, but it just cost me thousands of dollars in lost wear, and I got to get back to where I was before. So that selection of clays turns out to be really important. Everybody locks in that, and then what they want is that clay to come in every day to be the same. Does it come in every day the same? What changes? This all ties together. Really,
Seasons.
say again?
Seasons.
Seasons. Seasonal changes, the clay changes. Okay. Now, what changes is probably not the morphology, but the ionic strength of the system, ability to dissolve salts. If you sit out in the rain, and they're not going to mine the clay and set it in the rain, they're going to put it under a shed. The problem is they're still mining clay, whatever is in the mine is still getting washed, and then your ionic strength changes, and that changes your interaction between the particles. Can you compensate for it? Possibly. So, 1983, George Onoda, who was a faculty member here, it's far after that, he started here in 1993. Okay, and I know that because he and I started on the same day. And George, though, had a much longer career before he came here than I did, and so he introduced this idea 10 years previous to that, 1983, of specific volume diagram approach. He thought it had an application for the ceramic process. But it turns out he was right, but not in the way that it had been introduced. Okay, and he never pursued it past this. And we looked at that, and this is that diagram came out of his paper. What you get is that the packing efficiency, the density of that system follows the rule of mixtures with 1 over the density. Okay, so specific volume is 1 over the density. That's this term, and then this is linear with respect to mass fraction of components. Okay, so what you get is, this is, say, the volume of liquid, or the specific volume of the liquid, this is specific volume of the particle, and if you add liquid into a packed bed of particles, there's no change in volume. Overall volume stays the same. And so that means that this line goes to 0, and if you add a particle into a liquid, then the volume of the system decreases by the volume of the particle. So that's this, the skeletal volume of the system, if you will. And so this is the packing efficiency of the particle. And so if you change the packing efficiency, right, what happens is where these two lines intersect is the saturation point for the system. Right? So that's the amount of water necessary to fill the pore volume. That sounds great, except it's on a weight basis. And if I change the density of the material, that changes. The other thing is, if I take the powder as I get it out of the bag and I measure its packing efficiency, where is it? It's terrible, right? I mean, I'll get 20% packing efficiency of that dry powder out of the bag. That's not on, it's on this scale, but it's way up there someplace. So we actually argue that this scale changes in this fashion. So if I were to draw this diagram like this, okay, I have weight percent, mass percent water, and I look at the specific volume of the powder versus specific volume of water, for example. Here's 1, right? If I get 20% packing, my specific volume is 1 over 0.2, which is 5, which is way up here someplace. So if I look at it this way, right, I have the system, here's 1, right, that's that point up there. But here, I sit up there in the dry state. And if I do that math, and say I'm going to go here like this, and I go like this, down to 0, this goes to here, right? Then I'm looking at water content necessary to fill the pore space is huge. What happens is, as soon as I put that material in water, my packing efficiency increases dramatically. So really, this curve looks something like this, comes down like this, and then it goes, no, that's not quite correct. It actually comes down really low, something here. Right? So this dry, you cannot measure the packing behavior dry. You need to measure the packing behavior under the condition similar to what you're going to do in the process. If you have dispersion in, you have to measure the packing efficiency with dispersion. If you have ionic strength, you have to measure the packing efficiency with ionic strength. Turns out that that's very easy to do. And we have figured out a shortcut to doing so. Because what we have to do is we need this saturation point. Because nothing happens without saturation. Here's what we have. Here's an example. This is for 50% packing efficiency of zirconia, alumina, and clay. Now what's great about this diagram is that because of these differences, I need 14% water, 14.3% water to saturate a zirconia body at 50% packing efficiency. I need 20% for alumina, and I need 27% for clay. What does that mean? This means job security. Because this is immensely confusing. You look at a batch for alumina, and you look at a batch for zirconia, and none of the numbers line up. Right? So I have lots of work to do. Works out great. Okay? So if I look at an extrusion body, okay, the mass basis, this is just the saturation point for the same packing efficiency of these powders. 50% packing efficiency. So if you take had a small job, consulting job with a former student of mine, I told you the story, over in Horseheads. And his company had just bought a company that did hydrofracking, and they were stockpiling sand for fracking. So they use sand for, you go in the hydrofrack and you crack the bedrock, or it's not bedrock, but the shale formation. And then you stick little sand particles in there to keep the cracks open. It's called hydrofracking. Crack the matrix, and you put in called proppant. So you had 2 warehouses full of sand. Of course, it's not full of sand. They're like cones of sand everywhere. And he said, "I need to determine how much sand is here." And so I came out over and I saw him, and Judge Moore looked at me and took pictures. And, so we're buying this, and we need to know how much sand is here because it's an inventory issue. Blah blah blah. Okay, how do you do it? You cheat. I hired a surveyor to go in and map the sand piles and tell me how much sand is there. Tell me what the volume of the pile is. What do you need to know next? And packing efficiency. So we estimated there was something like 52,000 tons of sand, something ridiculous like that. And his estimates based on inventory and rail cars coming in and dumping sand at different sizes and stuff. So we went into the graduated cylinder, put the sand in, measured the packing efficiency. We measured the angle of repose, didn't need it. The surveyor came in, actually it's Emily Carney's husband was a surveyor. He came in and they surveyed this pile and came back with the volume, and we got that. We were within like 10 tons of what they, something ridiculous like that, ridiculously close to what they estimated that line to be. There's no way I could have the same problem. Survey, he was all about it. It was great. So packing efficiency for most systems runs about 50%. Not a bad place to start. So if you go here, for extrusion bodies, these are the batches done on a weight basis. Density of zirconia is 6, density of alumina is 4, density of clay is 2.6. And what you see is that these are all different. Okay, we do the same thing for casting bodies. It makes everything look, tape casting bodies, everything looks unique. These bodies don't make sense until, and even if I look at it this way, I require roughly twice as much water to process clay as I do for zirconia. Okay, and it's really awesome because it's so opaque. So what if we look at it instead on a volume basis? So instead of the mass being the x-axis, we do volume. So I have specific gravity then here, and this is the water content. But now I don't care what happens in undersaturated bodies. I want to start my analysis with the pore space between the particles is saturated with water. With this relationship now, the fraction of powder on a volume basis times 1 over the density of the powder, it says A, it should say P, and versus the fraction on the water basis times 1 over the density of the water, okay, gives me the density of my sample. But you get a curve because this is not a linear function, okay? But the difference is when I take this data right, and I correct it for density, now the curves all line up. And they line up perfectly because this is pore saturation. This is a point where the pores are filled with water. Nothing happens in this system below pore saturation for plastic forming processes, okay? That is why the shear cell doesn't work to characterize plasticity in the way that we would want. We learn things from the shear cell, but I can't take a plastic body and put it in the shear cell and say, oh, I know that this is going to be a good body for extrusion, because I will measure the same thing every time. I'll have a low cohesion stress in the system or a very small variation in cohesion stress based on conditions. But all those will have a zero pressure dependence, because now when you press on the system, you have water filling the pores, you get a hydrostatic pressure case, and there is no drag on the system because water is incompressible. So applying pressure does not increase the friction in the system, as long as my pores are saturated. So now what happens is that if I take now correct all the batch composition for volume, this is what happens. Suddenly, those batches would look so different. Now look exactly the same. So my amount of binder that I put in for alumina and clay and zirconia is the same. The amount of plasticizer is the same. And the lubricant and the intrusion body is the same. And yet my water contents are the same because the water content is dictated by filling the pore volume plus excess. So if you add up all of this, so your polymers, your binders, etc., are all contributing to volume. So if I bring in binder, I have 8% binder in the system on a volume basis. Okay, when I get done, I end up with 56%, okay, versus 50. So I have 6% excess liquid in the system. Okay, we could argue that the clay case may not be entirely correct because clays generate that excess volume automatically. I'm going to talk about that soon. Take acid in the same thing. Okay, now I'm 60%. Or I have 60, so I have 10% excess in the system. So we've defined these process windows. Extrusion, the excess liquid level is 6%, plus or minus 1%. So a plastic body requires 6% excess water. What does that mean? That's the amount of water that's over the amount of water necessary to fill the pore space. If it took me, if I got better packing efficiency and I got 60% packing efficiency, that window of 6% is still valid. I need 6% excess liquid in the system to provide room for the particles to move around. Tape casting is 10. Castable slump, this is essentially like vibratory casting or cements. You only need 3% excess liquid in the system to get flow, which is arguably dilating typically in these systems, but that's what you need. You need a little bit of excess liquid to provide room for particles to move around. Okay? It looks like this. I don't have castable slump on here, but here's my extrusion window and my tape casting window. It's my contention that that 1.2% variability in that window has to do with difficulties in measuring pore saturation. Right? So if I'm off of my pore saturation, I'm going to be off of my window for extrusion. Now I would go one step further if you're familiar with robocasting, 3D printing technology, right? Joe Cesarano is giving a seminar tomorrow on robocasting, as it turns out. If I was Joe, I would push this to be slightly oversaturated or have excess water in it to improve the adhesion of the layer that he printed a minute ago to the layer that he's printing now. By going a little bit of excess, not too much. You go too much, the system becomes sloppy. But you want to be on the upper side of that window potentially to improve the bonding between the layers, because that's an issue, right? Tape casting, same sort of thing. So that window doesn't change based on the material that I'm working with. Okay, this is a huge improvement in understanding of extrusion systems, because now I look at all extrusion systems as being the same. If you were in 203 ceramic processing, you don't recognize perhaps what a big deal this is, but I give you this information. You go into the lab and create an extrusion body immediately. You can vary then within that window, right? But you are able to walk into the lab and create an extrusion body. That did not happen before this. We would give you a recipe, right? There's no recipe. We tell you you need 6% excess water, What do you gotta do? You have to figure out the packing efficiency. Let's take one step back, right? What's the problem? Everything we do is on a weight basis. We have to convert to volume. If I have a 1% increase in water content in alumina, that's on a weight basis, that's 4% by volume. Okay, if I come back here and I'm sitting on, say, sitting at 4% excess, and I add 1%, I jump to 8, I can miss my window altogether for extrusion. And if I'm in zirconia, it's worse, right? Because I have a density of 5 or 5.6. Now one weight percent is 5 volume percent. I can blow right past the window. So if we go the other direction, right? I need 6% or excess liquid. How about in a clay system, right? Now what happens is that I have the packing to clay density is 2.6. I need 6%. I divide it by that 2.6. I actually need only about roughly 0.5% by mass increase in liquid in the system to provide plasticity. So it's my argument that in clay bodies, you get randomly oriented clay particles, right? And they're going to pack to a certain packing efficiency. But when I shear this system, I get alignment of clay particles, and that increases the packing efficiency with that alignment, producing the amount of excess water I need for plasticity. This is the intrinsic plasticity associated with clay, is that in shear forming, which is all the plastic forming processes, in shearing, create the excess water that I need automatically to give me plastic behavior. So I take that body and I work with it, and when I shear it, I automatically create the excess volume that I need to provide the plasticity. And it's intrinsic in the shape of those particles and alignment of particles. It's well documented that the particles align. And you can see it. I have an example that I should bring in. It's an extrusion system. And you can see that the outside inch is aligned clay, and the middle is roughly random, which also, by the way, tells us something about extrusion. I'm going to ignore rubber casting because I don't care. There's slump, and I'm going to go to this. Here is how you determine packing efficiency. Nestor, the guy who did pressure casting, came into my office and we were talking about the density of the system, and the way we used to do it, that you would take a slip cast body and then you would dry the body, and you would then introduce kerosene to fill the pores, and you would do a kerosene density, so you would saturate the pores by vacuum, do the dry weight, saturated weight with quick kerosene, then suspend it in kerosene to get a kerosene displacement, right? So your typical density through immersion, and I encourage you strongly to call it immersion, not Archimedes. So Archimedes is measuring the volume of water overflowing a bathtub. We're not measuring the volume of water, we're doing a mass. The density of the system is the dry mass divided by the saturated mass, designated by W, minus the suspended mass, okay? True, not a problem, right? That this, the saturated mass minus the suspended mass, is the volume of the sample, okay? So I get my dry mass divided by the volume gives me density. I need packing efficiency. So if I slip cast a body, okay, and then what I do is I take that slip cast body and I get the mass, saturated mass, by slip casting. That tells me then that I have a saturated body with water in the pores. Okay. If I dry that body, so I get slip cast and I get a saturated body. If I dry that body, okay, the difference, right, saturated minus dry is saturated minus dry. Leah? What's saturated minus dry? Tell me about the body. Right, this is the water. Now it's a mass, right? But knowing the density, I get the water volume. That water volume is my pore volume in the system. Okay? If I take the dry mass and I divide by the density of powder, that gives me the volume of powder. Right? So all I need to know is the density of the powder. How do I get the density of the powder? Well, I could guess. If it's aluminum, it's 4. If it's clay, it's 2.6. But I could also measure the density independently in a helium pycnometer or in a pycnometer method and get the density that way. Okay? And if I take volume of powder plus the volume of water, this is the total volume. And if I take the volume of water divided by the total volume, this is my pore volume. And this is then, if I take it times 100, I get a percent. Okay? And if I take the volume of powder divided by the total, I get the packing efficiency of the body. So this is fast. The only trick is that you have to figure out when that casting process is complete. So if you do it early, you have liquid slip left on top of the cast. Well, that's overestimating the water content. And if you let it sit there, what happens? Evaporation, you lose water, then you'll underestimate your pore volume. Right? How do you reduce the evaporation of water? How do you know that you're at the saturation point when you're done? So in slip casting, right, I'm pulling water out of the system by capillary action, and then that process stops when I run out of water. And the way that I could remove water from the pore structure is only by having a smaller pore associated with that, because the pore structure of the compact will prevent water from being removed by set capillary action. So all I need to do is reduce evaporation. If I cover my cast, right, and prevent free evaporation from the surface, what should happen is once I'm done casting, that my water loss is very shallow. My water loss versus time is shallow. And I have somebody working on that now. Somebody here working on that? There's somebody 3 or 14 working on that. Okay? How fast does water evaporate from the sample? If you look at Rehan and Hunter Pryor's thesis, they didn't do that. Their water loss is rapid. Okay? But what you're looking for is then at what point you hit saturation and then dry the sample. I don't need any dimensions. I don't even care if the sample falls apart in the dryer, right? Because it doesn't make any difference. I don't need an intact sample to measure this. I just need to know what the pore water was, which I get by the difference of the saturated minus the dry, and I need to know the density, the skeletal density, which I get from the density of the particle. So this makes it quick and efficient. So that, in a nutshell, is plastic forming process. Everything relates back essentially to this diagram here. So 3% excess for vibratory casting or cement. There's a lot of variability here, and a lot of variability here has to do with difficulties in making the measurement. I didn't go through it here, but I'll post this to Canvas, and we wrote an article about it. Okay. We haven't published it yet in a journal because I want to refine the extrusion and the tape casting and stuff. Hunter and Rehan got the tape casting thing figured out, and there's some other people done tape casting. It all fits. I need more data on extrusion before we go to publish. But this is the window. And it ties all the forming processes together. Okay. So plastic forming dictated by the amount of excess water necessary to fill the pore space. In clay bodies, when you go to filter press, right, what you do is you automatically go to that saturation point for randomly oriented particles. So the system automatically goes to the right water content for extrusion. Then when you put it in extrusion, shearing lines of particles and provides the plastic behavior for flow. So for us in traditional ceramic forming, that filter pressing step is critical. Okay? Because the filter pressing process gives me then a plastic body automatically. When we first started, well, not when we first started, we got a grant to transfer information learned in the Whitewood Research Center to industry. And I brought in Harry Stevens, who was a former professor here and then had gone to Corning, and he toured the factories. He came back and he was all excited. He said, did I tell you this already? They don't know the water content in the body. Did I tell you that? So we went on this elaborate thing of, let's measure the water content of the body. And the companies, turns out, they didn't care. The reason they didn't care is because water content was a response, right? And the fact is, if you change the raw material, or the packing changes a little bit or something like that, that water content as a response changes automatically in filter pressing. They did not need to know what the water content was, because it didn't actually affect them in the process. And I had not at the time put together this idea that water content had to be a response. That's something that came later, a few years ago. Water content's a response. When I changed the raw material particle size distribution, or I changed morphology, or I changed my degree of dispersion or coagulation, I changed that packing efficiency. Filter pressing automatically compensates for those differences, because you are applying pressure to the liquid only, and the liquid goes out, and the particles pack to their maximum density, or whatever density they're going to pack to. There's no shear associated with that packing. So you get the body out without shear, and then once you shear it, the volume concentration of particles or packing increases, and the amount of liquid that's expressed in that process gives you the intrinsic plasticity that you need. We have 6 minutes left. Should I do dry pressing really quickly? Yes. At least I think I should. Okay. Just so we can get out of this and go on to something more interesting. We also have a homework assignment, right? A couple of them. How are you doing on those? So, 1995, we held the first Science and Whitelist Conference. And the group from Spain, called the Spaniards, they have been doing an immense amount of work on dry pressing, okay, because of tile production in Spain. So the story is that the Italians started to develop automatic equipment for making tile. They became really good at it, and they sort of, more or less overnight, and of course a really short period of time, took over the global tile market. And they're building these huge presses, and they have the lower earth kilns. There's a couple of companies. Saki is a big one. Seti is another one. And there's a couple of others, and they build all this equipment. And then the Spaniards had a lot of clay, and they looked at what the Italians were doing, and they said, "We want to make tile. We got the resources." So the Italians happily sold equipment to Spain, and when they got to Spain, they took the Spanish clays. It didn't work well in the press, and so the Italians, of course, graciously offered to sell the Spanish clay, which was no point in that. I mean, the whole point of doing this is because they had clay. So they formed a research center called ITC, Instituto Tecnológico Cerámica, in Castellón, Spain, associated with the University of James I in Valencia, and they figured out how to make the Spanish clays work in the Italian presses. And the Spaniards, more or less, took over a large share of the tile market. So this group then, who had done all this work, they're working with all these companies that are building tile plants in Spain. And one time I was in Spain, and we were on the highway, and from the highway you can see the plumes from 18 spray dryers, 18 factories, all making tile from this little crest in the hills. You're out in the coastal plains, basically. You're in the orange groves and everything. And here's all these monster tile factories. Okay. So the Spaniards were interested in this, right? The whole deal for making tile is uniform die form. It doesn't have anything to do with pressing. In academia, we all like pressing because we can measure it. Okay, that's good. We can measure compaction behavior. And compaction behavior looks like this, and we're not going to get through this today. But I have some images, too, that I will show you. Okay. If I look at log pressure, I look at density, I get 3 regions. Okay, and so I can extrapolate this region down to P1, P2. Log pressure, remember, this is packing density of the powder, and then this is my maximum density. This is region 3, region 2, which are compaction region, region 1, which is simply the way the material behaves. P1 is actually the strength of the granules in the bed. There's no change in density with an increase in pressure up to a certain point. And then this is actually a spring back. This is elastic energy. So this is plastic to elastic transition. Okay, and when you get above a certain pressure, what happens if you store elastic energy, you start generating spring back defects. And we'll probably talk about that a little bit. So plastic, by the way, just for clarification, is really confusing because I have plastic deformation of metals. Talk about plastic deformation, it's about plasticity in bodies. Plastic is permanent deformation, and elastic is recoverable deformation. So the Spaniards looked at spray-dried granular size, and they realized that the flow behavior, which is on the y-axis here, is sensitive to the size of the particles. I put these images behind here, and the images don't really do us justice, although they do illustrate some things. If I have small particles, they don't flow very well. Okay, there's more drag in the system. I get to really nice, relatively large spherical particles. They flow great. Okay, and if I get out here to where the particles are large, it's not that they're spheres; it's that they become irregular, and those irregular particles don't flow well. So they said really clearly, we're going to be here. Now, you notice some interesting things here. The bagel shape, I call it, or the donut, is interesting because it's a problem. Okay, and then the goal is how do you get rid of it? We know how to get rid of it. Nobody wants to do it because it costs money. I got to decide it's important. Okay. So they figure this out, and then they have their moisture content contributions. So they have 2 parameters. You need the right size, you need the right moisture content. And then they looked at the spray dryer. Now the spray dryers here, okay, the spray dryers are ridiculously large. Okay, our spray dryer does. Actually, we figured out when I came here. There was Bill Walker. He worked for it used to be called Champion Sparkler. I don't know what it's called now. And Jim Reed, who was a professor here. He wrote Introduction to Ceramic Processing, Ceramic Processing Fundamentals, or whatever it is. And they did spray dryer, so they gave us the premise for the spray dryer. And several years ago, not that long ago, about 3 years ago, we were operating this window, and then we started to map statistical experimental design and spray dryer. And found out that we were down in this little corner, and we had all this space that we could increase our volume significantly. What can we do? We could probably do something between 5 and 10 kilograms per hour of material through the spray dryer, as opposed to 1 to 2. These guys, they're doing 10 tons an hour or something like that. Actually, I have numbers. Huge amounts of material going through the spray dryer. Okay? They're immense, 4 or 5 stories tall. Okay. Another thing about this, hot air is coming in. They're very, very clever. In Spain, there was a problem, infrastructure, energy problem, and the tile plants, by and large, helped that immensely. They set up cogeneration facilities. So there's a gas turbine on the upstream end of this, and that gas turbine is generating electricity, and the excess heat coming off the gas turbine goes to run the spray dryer. So then they're generating electricity they need to run the plant. What's left over, they sell back to the grid in Spain. That helps everybody. It's a great setup, cogeneration facilities in Spain. So they have a clay slip from the reservoir, gets sprayed into the spray dryer, and then they have their cyclone to remove small particles get through. So the material comes up this way, and then this is the exhaust, and small particles get sucked up in here. They get taken out with the cyclone, and then they go to a dust collector so that nothing goes out. And what we're seeing is the exhaust plume out the stack. That's the plume from the spray dryer. It's typically steam. So you see steam. Now you're in the arid countryside in Spain, so it doesn't last very long, but it is generating electricity. I'm going to skip this and come back to it on Friday when we meet again. Okay, these are the numbers I'm going to leave you with. 4, powder out, flow rate 10 to 30 metric tons per hour is what they're producing for granite. Staggeringly large. Right? And then what you're bringing in basically is 25 to 45 cubic meters per hour of slip, and then the number 2, the flow rate coming out the exhaust back, is is this difference. You're basically increasing the volume of air out of the system. So your air that's coming in is 25 to 45 cubic meters per hour. What's going out is 30 to 50. So you increase the volume of air leaving the system by, in this case, you would say 17%, right? If you take the difference, or 10% for 45 to 50, okay? That increase in volume is water evaporated from the spray or granule. And then last is you get granules out that are 5 to 7% water. That goes into the press. So, have a great day. I will see you on Friday at this time in this room. If that is too early, I will take a lecture because I'm a nice guy. See you.